A plane in physics is a two-dimensional surface, rather like the surface of a table. An inclined plane is a two-dimensional surface that is inclined to the horizontal. In this case, the angle of inclination is 30 degrees from the horizontal. Let us consider a stationary 6 kilogram mass resting on the incline. Because the mass is stationary, Newton's first law dictates that the net force acting on the mass must be zero. So what forces are acting on the mass? Well, the gravitational force acts on all bodies, and that is 60 newtons, because we have the case of a 6 kilogram mass acting vertically downwards. We can quite easily calculate the gravitational force by saying that it's equal to the mass times g. The mass being 6 kilograms, g always being approximately 10 meters per second squared, and so we have 60 newtons gravitational force. Now, obviously, if this were the only force acting on the body, we'll accelerate downwards. So, because the body is in contact with the incline, there is a force acting perpendicular to the surface that it's in contact with and away from it. That force is called the normal reaction force. So let's show it here. Now, if these two were the only forces acting on the body will obviously accelerate in the direction of the resultant force, which in this case is somewhere downslope. But we have already said that the net force is zero, so there is no resultant force. As the body tries to move downwards, the force that balances it to stop it moving downwards is, of course, that of friction between the block and the inclined surface. So these are the three forces that are acting on the block. If we add these three forces, we will get a net force of zero. One way to add them will be to use the head-to-tail method. So, for example, if we have the gravitational force added to the normal force, we place the vectors head to tail, and to that we add the normal force, we see that the triangle closes, and so we have a net force of zero. The next question that we need to answer is, what are the values of the frictional force and the normal reaction force? It was easy to calculate the value for the gravitational force, but the values of the normal reaction force and friction force will obviously depend on the inclination angle. There must be a downward component to balance friction, otherwise the block would be accelerating upslope. That downward component of force must be the resolved component of the gravitational force. We now need to resolve the weight force into two perpendicular components. One will be parallel to the slope, and the other will be perpendicular to the slope. To do this, we will draw a parallelogram with lines parallel and perpendicular to the slope, both at the tail and the head of the vector. And our components downslope and perpendicular to the slope are found by these lines here. What we notice here is that the component of the weight parallel to the slope must balance out the friction, and the component of the weight force that acts perpendicular to the slope must balance out the normal reaction force, and that is why the forces are stationary. So if we remove the gravitational force as the two components that it was resolved into take its place, this component must therefore be equal to the normal reaction force, and this component must therefore be equal to the friction force. So finding out the resolved components of the weight force will actually enable us to find the friction and the normal reaction force. The resolved components are easy to find using trigonometry. Since we know the angle there is 30 degrees, we can infer that the angle there is 60 degrees, and therefore the angle there is also 30 degrees, as this forms a right-angled triangle. Applying trigonometry, we can see that the resolved component downslope is given by the F gravitational sine 30, the magnitude of this vector times sine 30. In this case, it will be 60 newtons times sine of 30. And the magnitude of the component perpendicular to the slope that acts opposite to the normal is given by F gravitational cos 30. Doing the calculations, we see that F gravitational sine 30, which is this magnitude here, which should equal the friction, is 60 sine 30, which is 30 newtons. So the frictional force is 30 newtons. Likewise, this component here, the resolved component of the weight perpendicular to the slope, is F gravitational cos 30, and that should equal the size of the normal reaction force. So F gravitational cos 30 is 60 cos 30, which is 52 newtons. So the normal reaction force is 52 newtons. We can easily see that if there was no friction, or if we remove the friction from the surface, that the downward component of the weight acting downslope will actually act as a resultant force, and the body will accelerate downslope. In fact, we can calculate its acceleration. So we said that the net force accelerating the mass downslope is F gravitational sine 30, which is 30 newtons. So therefore, by applying Newton's second law, as the acceleration equals F net over mass, F net being 30 newtons, and the mass 6 kilograms, gives us an acceleration of 5 meters per second squared. Note that the normal reaction force is still balanced by the component of the weight acting perpendicular to the slope, and so there is no acceleration along this direction. The body will simply slide or accelerate downslope. If the frictional force did not balance the component downslope, if it were, for example, something slightly less than F sine 30, something less than 30 newtons, then there will still be a resultant force acting downslope, and therefore the mass will still accelerate downslope, but with something less than 5 meters per second squared. Let's look at an example. In this example, our friction will be 6 newtons. So looking at the net forces that are acting downslope, we have F gravitational sine 30, which is 30 newtons, and 6 newtons opposing it. So the net force is 30 minus 6, that's 24 newtons. That net force will cause an acceleration of 30 divided by 6, 30 minus 6, that's 24 divided by 6, and that is 5, no, it's not 5, and that is now 4 meters per second squared. Obviously, the larger the friction, the less the acceleration, until the friction force equals 30 newtons, which is the F gravitational sine 30, in which case either the block will remain stationary or will move at constant speed downslope as dictated by Newton's first law.